Hello and welcome to your Week 10 Solutions video for Week 10 of our discussion board, hosted by myself, Heather Barton, and Samantha Romero. This week, in Logic is Not Dry, we were challenged to create a circuit which would activate a dehumidifier given three conditions. One was that the air humidity in the room must exceed 20%, but also the container that holds the captured moisture must be less than 3/4 full. Likewise, when an override button is pressed, the dehumidifier will turn on regardless. From here, we can determine three simple propositions represented by P, Q, and R. P, the air humidity in the room exceeds 20%. Q, in regards to the container with the moisture. And R, being the override button. Likewise, with these values, we can now create a truth table with 1 essentially representing true for each and 0 false for each of our propositions, and an outcome table with 1 meaning that the dehumidifier would be turned on and 0 meaning that it would remain in an off state. Here, of course, we must remember that P and Q must both be true to turn on the dehumidifier. From the outcome table, or column of our truth table, we can create minterms, which are any row in which you could create an AND statement, or an AND expression rather, to generate one signal in the outcome, meaning that we could create an AND statement which would turn the dehumidifier on. So you can see we're left with 5 minterms, any of which could turn the dehumidifier on, such as P and Q and R, or P and Q and not R, or P and not Q and R, or not P and Q and R, or not P and not Q and R. With those minterms, we can create a circuit graph representing visually how each one of those would turn the dehumidifier on. Here you can see we've created a graph from circuitverse.org, and so it not only includes all of our and or and not gates, but it also gives a demonstration of how different values would run through the circuits using light green and dark green. If it's a little confusing, you can see that we've incorporated each one of our minterms just prior to the last OR gate. And then, of course, our final statement includes every single one of our minterms. Expressed a little bit more simply, we could use different values of P, Q, and R in multiple in order to create a larger circuit graph, but it's still the same circuit graph. You can see we have all the same minterms represented. Things are just a little bit more straightforward as we don't have different values overlapping one another. Of course, our statement is very large. We have some 11 gates that are going on. And if we wanted to simplify things, we might be able to do so using different logic or reasoning, but there's also a tool created by Maurice Carnot in 1953 known as a Carnot map. A Carnot map, also called a K-map, essentially starts with a table. In that table, you have all of your propositions listed along the top and along the side, and then we are able to mark each one of our minterms with a dot. From there, there's a simple rule. Multiples of 2, either vertically or horizontally or both, can be circled. From each one of these circles, we can make a deduction. So here you can see we have a yellow circle in the upper left-hand corner, and then we have a cluster of 4 that kind of goes across the sides. And if you could imagine those sort of connect around, because if we had written our table somewhat differently, those values could be right next to one another. And so we can circle them as a cluster of 4. From each, we can deduce which one of these values is always true within that circle. In our yellow circle, you can see that P and Q are true for each value that's been circled. So we know that P and Q can be incorporated in our final simplified design. Likewise, in the green circle, we can see that there's both P and not P, and both Q and not Q, but R remains the same. So we know that R alone can remain in our final simplified design, as R alone could turn the dehumidifier on. And so we're left with a final simplified statement of P and Q, or R, which would reduce our circuit graph from 11 gates to 2, which is pretty great. but we still want to check our work and make sure that we didn't maybe leave something out or misinterpret something. And so we can enter our simplified statement back into our truth table. Here you can see P and Q or R resulted in exactly the same truth table outcome as the original outcome column. This means that both our simplified statement and the outcome are equivalent. Thereby, our K-map is an excellent method to use in order to simplify complex equations.